We are working on finishing off implicit differentiation. And so I want to do some more questions of that type. And I also want to do a couple of examples of finding the equation of a tangent line. So first things first, let me just pick somebody to do implicit differentiation with. So this is question 12. And the guy I'm picking is deliberately ugly. And I'm going to show you two different ways to do this guy. And the first way I'm going to do it, oh, Zoom's went weird on me. Hold on a second while why does it do that? You know, it's so easy to distract me. Okay, I'll just leave you over there for the time being. Right, there are going to be two ways to do this thing. And the first way is pretty much just do it as it is. And then I'll tell you about the second way after that. If I am going to differentiate the square root of anything, then I need to turn it into a half power. That just goes without saying, right? There's no way to avoid that. So this question is ugly times 2. So bear with me. That's, you know, you get what you get, and that's fine. We just have to realize that it is ugly. So what I'm going to do now is differentiate, right? This fella here is essentially a chain rule. So when you differentiate it, you get 1/2 x plus y to the negative a half, right? So it's a half something to the negative a half times the derivative of the something. Well, the derivative of x plus y is 1 over dy by dx. And on this side, it's a lot cleaner. It's 3x squared and then 3y squared dy by dx. So far, so good. Now, I know that my goal is to get dy by dx, and that's where we're going to end up. But I have some really messy algebra to take care of. I do not like x plus y to the negative a half. It is not going to make my life easy. So first thing I'm going to do before I even worry about how to get dy by dx on its own is I'm going to write this thing as 2 over the square root of x plus y. Are you okay with a negative a half power coming downstairs and turning into a square root? And this 2 just joining it. Now, all I've done from this line to that line is get rid of that negative a half power, and it's got a little bit uglier, I agree. It's messier than it was. I'm now going to put in an extra line over 1, because what I'm now going to do is cross multiply. So this times this. So what do I get? I get 2 lots of the square root of x plus y times all of this stuff equals 1 times this guy. Okay, now we need to figure out how we are going to isolate dy by dx. And we take, we do it one step at a time, and each step we get a little bit closer to our final destination. What do you think would be a good idea to do to the left-hand side to get a little bit closer to where we want to be?
Distribute.
I would agree. So that times that gets me 6, and x squared, square root of x add y, and that times that gets me a 6, a y squared, square root of x add y, dy by dx, and the right-hand side is still the right-hand side. Looking good? Okay, every time we do something, it gets a little bit closer. What should I do now?
Move all the derivatives over to one side.
Okay. Can I move this guy over to here? Right, this dy by dx over here by subtracting it from both sides. And while I'm at it, maybe I should get rid of this guy and get it over here by subtracting this from both sides. So if we do both of what I just said, if you subtract the dy by dx from both sides, you'll get that. And if you subtract the 6x squared square root of x add y from both sides, you get that. Every step gets a little bit closer. In fact, when you do these questions, the last two steps pretty much end up being the same for everybody. So what's the next step? There are only two steps to go. What's the second last step? What do we do here?
Pull that dy dx out.
Have you noticed that pretty much, sorry? Yeah, you're right. I was going to say, have you noticed pretty much every question that you did that was a difficult question, right? That had more dy by dx's in it. Didn't it involve pulling out dy by dx as a common factor, right? That was the second last line. And what was the last line then? What's the last thing we do and we're finished? What do I do now to get dy by dx?
Divide both sides by 6y squared, square root of x plus y, or the factor on the left.
I know exactly what you mean, yeah. And I'm not going to make any attempt to make that pretty, because any attempt that I did to make that prettier, it would look even worse. So we'll call that done. I took a whole page and the answer was downright ugly. Agreed? There is nothing pretty about that answer. It's messy. It was messy when it started. It was messy when it finished, and there was nothing in the middle to make it even better. But it worked. That is the derivative of this implicit curve. And I promised you that there's two ways to tackle this question. I have a rule called just because you can doesn't mean you should rule. You remember that rule? Just because you can doesn't mean you should rule. Now, I could, and I've done it, so it's possible, I can do it. I found it by just taking it as it was and just doing implicit differentiation. Of course, sometimes, not always, but sometimes you can make your life easier. Is there anything algebraically I could do to both sides that would make this guy a much easier expression to work with?
Square them.
Okay, now if you square both sides, would you agree that mathematically it's the same information? You square that side, you square that side. Now, if I FOIL this out, it becomes that. Now let's look at the choices. I did this guy, ugly and messy. Would you agree, although I'm not going to do it for time purposes, would you agree that that is going to be much easier to differentiate? And isn't it going to be much easier to make it look prettier at the end? Because isn't there not a square root in sight here? And so whatever answer we get is just going to be of x cubes and y squareds in it, and that's okay. And when we get the answer to that, which I've said I'm not going to do because I don't have time. So this is not the right answer, but I'm just pretending it is. It might be something like that. And there is a curiosity that the derivative of that is this ugly guy with a square root. And the derivative of the same thing is a totally different looking derivative. Yet these are the same mathematically. They are equivalent to each other. Now, you don't normally get that in good old-fashioned y equals a function of x world, right? If you have y equals a function of x, doesn't everybody's derivative, if you do it right, end up looking the same, right? You all end up with the same answer. But when you have implicit differentiation, it is quite conceivable that depending on the algebra that you use to solve the problem, you could end up with quite different looking answers, but they are both correct. Analogy. Do you know in trig, you can have two different expressions that look totally different from each other, but they're actually equal to each other as far as trig's concerned, right? They're equivalent. So it is possible. So what am I getting at here? You might look at a implicit differentiation question like number 12. And you might just blindly do the process. And if you do, I'm okay with that. It's fine. You're right. But just on the off chance, look at the question again, just in case you could do something better. Here's an example of a question where I would probably do it differently. Do you know if I had to do this using implicit differentiation, if I left it the way it is right now, wouldn't that be a quotient rule? Wouldn't this be a quotient rule? Wouldn't that be another quotient rule? Can you just imagine how ugly algebraically that process would be? Now, could I do it? You know, not saying you couldn't. It's possible. You would leave, you know, you'd lose a year of your life through it, but it would be possible. Or I could cross multiply, then distribute it. Would you agree that that would be a much easier expression to find the derivative of? Right? Nice, horrendous. So just be on the lookout. It's not a common situation, but it could happen, right? So when it does, if you can see it, go for it. It might mean that your answer isn't the same as WebAssign's. WebAssign might have this ugly answer, but you took the other pathway, right? And you have this answer. If you do it the shortcut way and you're convinced that you did it correctly, but WebAssign is saying, nope, I don't see it, you're not right, shoot me an email and I'll just give you the points on homework. Okay, any questions so far? I'm assuming that we're good then for the time being. So I want to do two questions. Oh, darn it, and Spice. Why is that being a pain? There we go. Zoom was being a pain. Right. We're going to find the equation of a tangent line. To an implicit expression. I don't like calling them functions. I'm not really functions, most of them. And the guy I'm picking for the first example is one of my own. Suppose you're being asked to find the equation of the tangent line to this curve at the point 1, 2, right? That's a pretty common question. Don't they very often give you a couple of questions at the end? Find the equation of the tangent line, right? So they did it when you did the product rule and the quotient rule and the chain rule. We're going to do it with implicit as well. There are two steps. Isn't the first step find the derivative so that you can get the slope of the tangent line? And then the second step is y minus y1 equals m brackets x minus x1, right? The point slope equation. And that's us done. So this guy here, 3x squared. This guy here, 2y dy by dx. This guy here, 2. And what's the derivative of the number 7? Yeah, nothing. In this case, we don't really have too much to concern ourselves with. Subtract 2 and 3x squared from both sides, and then divide by 2y. There's our derivative. Now, to get m, the slope of the tangent line, we evaluate the derivative at this point. Now, there's just a tiny difference. Normally, don't you just use the x coordinate, you know, when it's y equals f of x kind of story. But here, we're using the x and the y coordinate. So it's -2, take away 3 times 1 squared, all over 2 times 2, which gives me -5/4. Are you happy about how I got the slope of the tangent line at the point 1, 2? I plugged x equals 1 and y equals 2 into here, right? That's the derivative at that point. So that's the slope of the tangent line. I can now do the point slope equation to get the equation of the tangent line. So it's going to be y take away 2 equals -5/4 x x take away 1. We'll pause there for a minute. So it's -5/4 x, add 5/4, -5/4 x, add 8. So it's 13/4. Okay. So the equation of this implicit curve at that point, the equation of its tangent line is this fella here. Pretty standard process, right? Find the derivative, evaluate it at the point, and then use the point slope equation. Let me show you something that I've already done. You know these guys? You can check them out in Desmos. You can type in implicit curves into Desmos. That's kind of cool. And of course, there's the straight line. And can you see that that is actually a tangent point at 1, 2?
I had kind of assumed you would have to solve for y to graph them.
You would have, but isn't Desmos your friend? Isn't it nice that it can do that? Because not all implicit functions can you rearrange as a y equals. So it's great that you don't need to. So just type it in as sine of x plus y minus y, whatever it is, and let Desmos do it. Since I've got this guy up and running, I want to do something that's been just for me, basically, my curiosity. I've seen some of these weird ones, and I wonder what they look like. So sine of x, oops, let me try that again. The sine, there we go. The sine of x plus, say, the cosine of y equals 1. I did not expect that, but it's kind of cool. That implicit expression generates an infinite number of, let's zoom in on one. It's not a circle. I mean, if you look really carefully, it's not circular. Would you agree it's kind of squished a little bit, for want of a better word? Can you see how versatile implicit expressions are? How you can generate things that you couldn't do as a y equals function of x, right? There's just no way that could be done, because for starters, it's not a function, right? But that was kind of cool. I like that. So that's kind of satisfied my curiosity, because I was wondering what some of these darn things looked like. And now I can actually just go to Desmos and find out. A lot of the time it won't be anything that interesting, I expect, but then again, oh, that was rather strange. Now, excuse me, promised you 2 examples of that. As soon as I get my act together, I will do it. Close so many windows, it's hard to remember which ones are left. So the guy I'm going to do is question 15. It's the equation of a tangent line, and I've chosen this one because of its ugly fractional powers. And this is the guy, and we're going to find its equation of the tangent line at that point. And I am going to take this guy and make him look like that guy. Let's see, you're happy with that first. Are you happy that -3 square root of 3 could also be written as 3 to the power of 3/2? Are you comfortable with that, or do you want me to show you why that is the case?
I think I'm okay with it.
Okay, so you might say, well, why am I doing that? The reason I'm doing that is because of these guys. You know, if the expression's in fractional powers, it's probably a good idea just to make everything fractional. It might make the algebra later a little bit cleaner. I'm hoping it does. I've done this one before. So multiply by the power, reduce the power by 1. No surprises there. Multiply by the power, reduce the power by 1, finishing with dy by dx. And would you agree the derivative of 4 is just 0? So nothing too surprising. I'm not going to do anything with the fractional powers yet, but I am going to subtract the 2/3 x to -1/3 from both sides. I am then going to divide both sides by y to the -1/3. Okay, we need some work here. I don't like the look of this answer. I want to try and simplify it as much as possible, because that's going to make my job towards the end a lot easier. So tell me anything you can see that could make this prettier.
Cancel the 2/3.
I like the thinking. And if I do that, I'm going to be left with that, which is definitely prettier. One more thing. Anything else you could do to this question?
So you could invert that x and y by doing reciprocal, or their powers would be 1
Agreed.
over
Right.
x to the 1/3.
I was going to tell someone to duck there. That aircraft looked like it was going to hit the place, wherever you are. So we got this guy. Are you happy about negative powers going the bottom and negative powers on the bottom going the top? Right. Okay. I'm going to leave it like that. And why? Isn't there a rule in style points that says make it look like the original? You agree it looks like the original. So I'm good. So I now need to find the slope of the tangent line. So it's going to be the value of the derivative at this point here. So it's going to be negative y to the power of 1/3 and x to the power of 1/3. Okay. 1 to the power of 1/3 is really the cube root of 1. So that's 1. What's this guy? Well, negative 3 to the power of 3/2, all raised to the power of 1/3. You essentially multiply these together, right? And what you're going to get is a negative 3 to the half. And two negatives make a plus. And that's just the same as 1 over the square root of 3. And I guess I could call it 1 over 3 to the half. I like 1 over square root of 3, so I'm keeping it. No, I don't. Change my mind. Let's be consistent. Right, everything else was fractional powers. Might as well make this a fractional power. So y minus y1 equals m brackets x take away x1. Going to use that as my y coordinate. And x, oops, take away that is add it. And this guy is 1 over 3 to the halves. So what do I get? Y minus 1, 1 over 3 to the halves x. Oh, that works quite nicely because that times that gets you 3. If you take this and this, you subtract a half power, you get 3 to the 1, you get 3. That's quite nice. And so you get 1 over 3 to the half x, add 4, and that is correct. Or if you don't like 3 to the half, you could do that guy, I guess. It's just the same thing. And we're finished. So I think leaving things in fractional powers probably was worth it. Right? It just made some of the number crunching a little bit easier. Hopefully, any of the steps I've done, you can double check them. I mean, that times that, if I write it down, that times that. It's really, that's what I was doing, right? Okay, that is implicit finished. Any questions? Okay, then for the next 20 minutes or so, a little bit less than that, we're going to look at our next section. This is not going to be in the homework, and it's not going to be in the test, but I want to get a head start because time is important. And we are going to look at try to spell logarithms here. Actually, 3/6 has got logarithms and inverse trig functions, but we're going to look at derivatives of logarithms. Now let's start off with what is the derivative of log x? Well, the short answer is right now, we don't know. We're going to find out in a minute, but we don't know right now. What do we know the logs of? Well, we know the logs of any power of x you like, right? Power. We know the log of e to the x. And we know the log of the 6 trig ratios, right? Sine and cosecant and things, right? But right now, we don't have log x. It's a kind of missing. Its derivative will be a surprise. Well, to most of you. Did you think the derivative of log x was going to be 1 over x? Does that look, maybe you didn't know what it was, but you probably wouldn't have thought it was that. Agreed? 1 over x, I know it could have been, right? Who knows? But you would expect something weird, right? Not something as plain as just 1 over x. But nonetheless, it is. But when I tell you things like that, isn't it magic? I just told you it is. Trust me, it is. You're good. So let's prove it to you. You don't need to know this proof for a test question or anything, but I think it's worth just to see how they come up with that answer. Right, I'm going to write the natural log as a log to the base e, because that's what natural log is. And when you did logs in 141, whatever, 6 months ago, a year, whenever you did it, you could convert things from what are called logarithmic form into exponential form. I called this the circle of life, if you got me. E to the power of y equals x. That's why I call it the circle of life. So e to the power of y equals x. Do you vaguely remember doing that? Right? Logarithmic into exponential form. So this guy is the same mathematically as this guy. I'm now going to differentiate this guy using implicit differentiation. Well, e to the y gets you e to the y times dy by dx, and the derivative of x is 1. And now I'll divide both sides by e to the y, and I'll get that. And you might say, but you told me the derivative was 1 over x, and it's not 1 over x, it's 1 over e to the y. Wait a minute, isn't e to the y equal to x? Which means then that you could write this guy as that. Now, does that make you feel a little bit better that it's not magic? That the derivative of the natural log is in fact 1 over x. Surprising as it may seem, that is what it is. So what we're going to do for the period of time that we've got left, apart from the last few minutes, is we're going to do some derivatives. So, suppose I want to find the natural log of that guy. Then the key word here should be chain rule, right? It's a log of something. So chain rule. So its derivative is 1 over the something times the derivative of that something. And then make it look pretty. Suppose you wanted to differentiate that guy. The magic word here would be product rule. Do you see a product? In this case, let's use dy by dx notation so we don't get too caught up with just one notation. Differentiate this guy, you get 1. Leave this guy alone, you get natural log of x. Leave this guy alone, you get x. Differentiate a natural log, you get 1 over x. This is log x, and this is 1. So the derivative of x log x is this guy. Now let's do the derivative of ten. Now, this is an example of just because I can doesn't mean I should. Now, could I do this answer just as a chain rule inside the chain rule? Of course I could. Wouldn't it be 1 over ugly guy times derivative of ugly guy? Wouldn't this ugly guy be a chain rule inside the chain rule inside the chain rule, right? I would get that, right? And it would work, and I would get the right answer. Unless I realize that I can rewrite it like that. Do you remember the 3 laws of logs? Oh yeah. Wasn't there one that said the log of a power can be written as a power times its log? You know, like the log of a cubed can be written as 3 log a. Remember that rule? It's the 3rd law of logs. Now, by writing it like that, isn't the derivative 10 log of something? So it's 10 over something times the derivative of that something. And now, very clean, very easy to do derivative. If you left it like that, wouldn't it be a chain rule inside a chain rule inside a chain rule, and would be quite messy, and you'd have to do a fair amount of algebra, but eventually you would get that. What about this guy? What about this guy?
Same thing, but with 7 halves.
Nailed it. I hope you all agree that that's much easier to differentiate than that would be. If you try to do that, are you already cringing on the square roots and 7th powers and chain rules inside chain rules with fractional powers all over the place and things having to cancel and combine, and God, you'd be there forever, wouldn't you? I guess you could do it, but I wouldn't want to. In this case, the derivative is 7 halves log of something, 7 halves over that something, times the derivative of that something. Those two get you 7x over x squared plus 1. Isn't that rule, just because you can doesn't mean you should rule, a good rule to be on the lookout for? Okay, I got a question in front of me. Do I have to use it the way it's written, or could I do something to make it an easier question to answer? Right. Remember we did, lost it on time there. Yeah. Remember, could I do this guy as implicit? Sure I could. If I left him like that, it would take me a day. Could I change it to something that's much easier to deal with? If you can, do it. Could I get the log of this guy? Sure I could. Could I get the log of that guy? Of course I could. But could I do it better? Could I do it more efficiently? That's kind of what the rule, just because you can, doesn't mean you should is, right? It can be used anywhere, right? So if I see math and I'm looking at a question, there's always a little click going on saying, okay, just have another look. Is that the best I can do? Is there something I could do to make my life easier? A lot of the time the answer is no. There's nothing you can do. You just got to do what it's in front of you. And that's fine. Majority of the time that's going to be the case. But now and again, there's a little bit of algebra here, you know. Hey, that might make my life easier. Let's do it. I'm going to finish this here, and then the last few minutes we're going to talk about your test and so on. Is there anything on this that you've got questions on before I kind of close the door on it for a while? Okay. So first thing, you do know that tomorrow is a non-class day, right?